Let's jump right in. Today, we're unlocking the engineering toolbox to look at the massive, ground-shaking, heavy machinery that literally shapes our modern world, metal forming equipment. If you've ever stood in a factory and wondered exactly how a giant, thick slab of steel gets transformed into a sleek automotive body panel or a high-stress aerospace component, you are in the exact right place. We're looking at the physics, the machinery, and the sheer power behind metal forming.
Just to ground ourselves, what exactly are we doing when we talk about metal forming? We're producing mechanical components through plastic deformation using applied forces. That's the textbook definition, right? But the actual engineering challenge here is absolutely wild. We are forcing solid metal to yield and plastically deform into entirely new geometries, all without breaking, cracking, or losing its structural integrity. Doing that requires immense power, but more importantly, it requires incredibly precise control.
Here's how we're going to break this down today. First, an introduction to the machinery. Then, we'll hit the forging hammers, hydraulic press machines, and mechanical and crank presses. After that, we'll get into equipment selection and design, and finally, look at some real-world industrial applications.
All right, Section 1, Introduction.
When you look at the sheer scale and variety of forming machinery out there, it can be pretty overwhelming, but we can broadly group the main equipment into what we'll call the Big Three. We've got hydraulic presses, mechanical presses, and hammers. These are the absolute workhorses of the industry. They handle everything from delicate sheet metal forming and bending to heavy-duty bulk forming and hot forging. And as an engineer, selecting the right machine from this lineup is literally the very first critical decision you have to make.
Let's move on to Section 2, the forging hammers.
The basic operating principle of a forging hammer is as simple as it is violent. It relies entirely on sudden, repeated impact motion. The machine is essentially converting the kinetic energy of a massive falling ram directly into deformation energy the split second it strikes the workpiece. And of course, that workpiece is supported from below by a heavy anvil, so the energy actually goes into the metal, not the floor. These hammers are usually classified by whatever mechanism lifts that ram, like gravity, compressed air, or steam. And you'll see them heavily relied upon for hot forging operations, where the metal is preheated so it's a bit more forgiving before the strike.
You can really see the mechanical linkages at play with these lifting mechanisms, using things like boards, chains, and cables. An electric motor does the heavy lifting, pulling that massive ram upward and storing all that potential energy. Then, the mechanism just lets go. Gravity takes over. The mass of the ram, multiplied by gravity and the drop height, delivers a massive, explosive release of kinetic energy right at the moment of impact. It's a sudden, brute force approach that is perfectly tailored for shaping thick, hot metal.
Section 3, Hydraulic Press Machines.
Now let's contrast that violent impact with the hydraulic press. The entire secret to this machine lies in Pascal's law. You probably remember this. Pressure applied to a confined fluid is transmitted equally in all directions. So a relatively small force applied to a small piston area creates immense pressure within the fluid. When that pressurized fluid then pushes against a much larger piston, it translates into a massive but highly controllable forming force. It's essentially fluid mechanics acting as the ultimate force multiplier.
Thanks to that hydraulic principle, these machines give us some serious engineering advantages. The biggest one, they deliver a perfectly consistent forming force throughout the entire length of the stroke. The ram movement and speed are totally under your control, and you can generate force capacities that are just off the charts. We're talking tens of thousands of tons. This slow, steady, customizable pressure makes hydraulic presses absolutely ideal for deep drawing, bending, and compression forming. If you tried to use a sudden hammer strike for those operations, you'd just tear the sheet metal to shreds.
Which brings us to Section 4, Mechanical and Crank Presses.
Let's walk through the exact power transmission chain of a mechanical crank press because it's a really elegant mechanical system. It starts with an electric motor generating power. That motor spins a huge, heavy flywheel to store rotational energy, which is absolutely crucial for keeping the momentum smooth when the machine hits the metal. A clutch then engages a crank mechanism, mathematically converting that continuous rotary motion into reciprocating linear motion, just straight up and down. Finally, the slide, or ram, delivers the stroke, driving the die into the workpiece to shape it.
When you map out the kinematics of the crank slider mechanism, you can see exactly how rotary motion becomes linear motion. Now, because this is a fixed mechanical linkage, the stroke length is set in stone. That ram is going to move precisely to the exact same bottom dead center every single time it cycles. This creates an incredibly fast, rigid, and repeatable motion. That's why crank presses are the go-to choice for rapid stamping, punching, and blanking operations where you need to churn out millions of identical parts.
Let's transition to Section 5, Equipment Selection and Design.
So how do you actually choose? The selection process starts by matching the machine's physics to the material's needs. Hammers give you high kinetic impact, but they shake the whole factory floor. Hydraulic presses give you that long, constant, high-pressure stroke, but they're relatively slow. Mechanical presses offer blisteringly high production rates and fixed strokes, but their force actually varies depending on the crank angle. Matching these specific motion profiles to your final product is really the core of manufacturing engineering.
Once you've picked your machine type, you have to nail down the critical design parameters. You've got to calculate the precise forming force to figure out your required machine capacity. You need to know your stroke length because that dictates the maximum depth of your draw. Your working speed impacts material flow and your overall factory production rate. And of course, you have to calculate torque and power to size your motor and ensure the structural strength of the machine frame can actually withstand the insane forces it's generating without snapping in half.
And this is where the rigorous mathematical analysis kicks in. We have to apply statics and the strength of materials to calculate the load, torque, and bending moments on the crankshaft. A really important detail here is that the bending moment actually changes depending on the crank angle. The force isn't static, it's highly dynamic. Engineers have to calculate these forces at their absolute peak to make sure the gears, the transmission, and the crank itself don't suffer a catastrophic failure while under load.
That need for structural strength brings us to frame design. The open C-frame is super popular because it's open on 3 sides, which is fantastic for operator access and automated material feeders. The downside? Under super high loads, a C-frame can actually flex and bend open slightly. So when we're dealing with massive forces, we upgrade to the enclosed O-frame, or a 4-pillar structure. In heavy industry, structural rigidity is everything. Today, we rely on advanced CAD and CAE simulations to evaluate force distribution and optimize these frames. The goal? Keeping allowable elastic deformation strictly limited to just 1 millimeter per 100 tons of force. Now that is rigid.
Finally, Section 6, Industrial Applications.
The scale of how this machinery is used in the real world is just staggering. Mechanical and hydraulic presses are working around the clock right now, stamping out the automotive body panels for the car sitting in your driveway. Massive hammers and presses are hot forging critical, high-strength titanium components for the aerospace industry. They're making heavy machinery parts and everyday consumer sheet metal goods. And crucially, all these concepts are actively tested in university laboratory settings. Through specific lab experiments, engineering students actually get hands-on experience, identifying components, observing these massive forces in real time, and evaluating machine performance parameters for themselves.
As we wrap up this explainer, I want to leave you with a thought about the future of this field. We have thoroughly mastered the mechanical, the hydraulic, and the kinetic. But as our manufacturing world shifts toward increasingly advanced, difficult-to-form materials, things like advanced titanium alloys and complex carbon composites, how will these traditional metal-forming machines need to evolve? Are we looking at smarter sensors, hybrid drivetrains, or entirely new physical principles? It's a fascinating challenge for the next generation of manufacturing engineers. Thanks so much for joining me on this deep dive into metal forming equipment.